Hi everybody. Today I'm going to talk to you guys about work, your favorite thing. In physics and in mathematics, work has a slightly different meaning than it does in your everyday life. Like, for example, you could talk about how you did a lot of physics work last night, or you went to work in the morning. Those are all things that you wouldn't say in the physics realm because work has a very specific mathematical definition. And so let's talk about that here real quick. So if we take a look at it here, work is, again, derived from Newton's second law. So you can start to see that Newton's second law is kind of a critical piece here. And this is why it's often considered the foundation of all classical physics. Now, if you remember before when we had our last unit, we started off by giving you a formula that looked like this. The force times the change in the time is equal to the mass times the change in the velocity. Hopefully you remember that. And this was the impulse side, right? J is the impulse side, and this was the change in momentum side. So we derived this from a couple of formulas, including one of which was Newton's second law. And then we used one from Unit 2. Now, we're going to do the same thing, and you're going to see we get a slightly different result. If we pick a different starting point, other than Newton's second law, we're going to pick a different motion equation to plug into it. And so I've chosen here the no time formula. So you're already going to see that this time feature right there, which we used in impulse, is not going to be a factor when we talk about work. So as I plug this in, the first thing I have to do before I plug it in is to solve it for A, because the A value right there we go, is going to be my entry point. So that's where I'm going to access this formula for right there. I'm going to go ahead and try to plug everything in to that A spot. Okay, so let's take a look at it here. If I solved this no time formula, which is what I call it, for A, I get this, which is ugly. I know, it's pretty hideous, but there it is. 1/2 times quantity v2 squared minus v1 squared, so that's the final velocity squared minus the initial velocity squared, all divided by the change in the displacement, or the change in the position. And so I plug it in here, so I take this and plug it in right there, and I end up with this yucky looking formula right there. Now, I can make it a little bit better by multiplying delta x on both sides. So if I multiply both sides by delta x, I end up with something that looks slightly better, and that's this right here. And so this, I'm going to put a little star by it so you remember it, is what we call the work kinetic energy theorem. Now remember, this was the impulse momentum theorem, and so you can see that they kind of look similar here. You've got on this side F delta x, which is the force times the displacement. And here you've got F delta t, so you get the force times the time. And as you might imagine, just like the force times the time was the impulse, the force times the displacement is going to be something else as well. And so I'm going to, there we go. I'm going to go ahead and block that off and tell you that that is something we call work. Work is the force times the displacement. It's the force that you apply times the displacement, the amount of distance that you apply it. So you might see somebody else write it like F times D. In math class, you might see it as F times R. All of those things, sometimes even F times S, S for delta S for change in the position. All of those things mean the same thing. So just kind of keep that in mind. Don't let that freak you out. This is just how far you're applying that force right there. So again, you can see it's a parallel to this. Now there are some differences. You might notice that impulse is a vector, and I've written the big W for work as in italics there, and so that signifies that it's a scalar. So we are absolutely not concerned with what direction the work is being done in, whereas impulse we were. Also notice that displacement is a vector and time is not, and so you're starting to get the idea of how we multiply vectors together. It kind of gets a little bit more complicated. Work is measured in newtons times meters, as you might imagine. But for simplicity's sake, because we use work and energy a lot, we have come up with a derived unit for it. And it's right here, and it's pronounced joules. Kind of like jewels, like a pirate would have in his pirate chest, but not obviously written the same way because it was someone's name, right? James Joule. And it's newtons times meters. So work and energy both are measured in joules like that, and I signify it with a capital J. So you can already start to see here we're going to have some problems because capital J is impulse, capital J is joules. Later on we're going to see capital W is work, capital W is also watts, and so we have to be careful about our units and our variables. Now one other thing we have to be careful about is that this vector and this vector need to be either in the same or in opposite directions. In other words, they have to have either 0-degree angle between them or a 180-degree angle between them. Why is that the case? Because we have to see here that the force is actually causing the object to move that distance. So if I have a box, let's say, and it's on the ground, and my little brother is pulling upward on it, and I'm pulling to the side, like so, and the box moves from this position on the floor to that position on the floor, which one of us caused that? Is it my little brother who's just being annoying, or is it me who's trying to pull it in the direction that it's going to move? The answer, of course, is that it's me, right? So this force does not have any bearing on this change in position right there. It doesn't cause it. And so did this person do work right here? Right? Even though my little brother might be sweating away, he's pulling so hard, he's straining every muscle in his body to try to pull that thing up. If it doesn't go up, if it doesn't move in that direction, then there's no work that's being done. Whereas I could be pulling very lightly in that direction, and if the box moves in that direction, then it's probably a pretty good indication that I was the cause of that. And so I caused the force, I caused the force, and so then I also caused the displacement. And therefore, it must be my work, right? So it's really about the ownership. And so so direction is important for those. And here I put a little infographic here. So you can see, in this case, the person is sliding this box across the table or across the floor. The direction of the force is this way. The direction of the motion is that way, so obviously work is being done. Yes, okay. When you're lifting a backpack, though, backpack hangs upward off of your shoulders, right? Your shoulders are applying an upward force. Sorry. But if you walk forward, that upward force is not the cause of the motion forward. And so you can see that doesn't work. And then you can go through the rest of these. If you have any further questions on it, let me know. Thanks for watching.